Not all forms or energies of radiation are equal when one compares their ability to harm or penetrate our patient's tissues. This is where an understanding of the concepts embodied in linear energy transfer and relative biological effect come into play. Here we have an X-ray tube, a collimator, and a patient. The technique is set so that the patient is exposed to a 30 kilovolt collimated X-ray beam. As the beam traverses the patient, some of the patient's tissues are ionized and subsequently damaged. I've indicated these ionization events with markers to highlight them. Also note that the energy of the X-ray beam is so low that little or no radiation penetrates the patient's anatomy. These ionization events are placed where the X-ray beam causes damage to the patient's tissues by ionizing the atoms in the cells. Also, the beam is essentially absorbed by the patient's tissues, and little radiation penetrates the patient. The beam is said to have a high LET because it interacts more often inside the patient. This slide depicts a mass of cobalt-60 held inside a lead enclosure. Cobalt-60 emits a couple of gamma rays, one at 1.17 and the other at 1.33 mega-electron volts. Rotating the inner shield exposes the cobalt, and the patient is exposed to the radiation as in a therapy treatment. Rotating the inner shield back to its home position stops the radiation exposure to the patient's tissues. Notice the pattern of ionization effects in the patient's anatomy. Let's now compare the pattern of ionization events in the two instances. In the 30 kV instance, the ionizations are more numerous and spaced closer together. In the instance of the cobalt-60, the events are more spread out and there are fewer of them. LET stands for linear energy transfer, which measures the amount of energy deposited per micrometer of the patient's tissues. The higher the LET, the more damage or ionization that radiation does to the patient's tissues, and less penetrating the radiation is overall. LET is the amount of energy deposited per micrometer of tissue. The energy is measured in kilo-electron volts, and the micrometer is 1/1,000,000th of a meter. A quick summary of factors that affect LET are listed below. LET is most affected by the kind of radiation the patient is exposed to. If the radiation consists of charged particle or particles, the LET of the radiation will be very high. Alpha particles have a +2 charge and are very damaging over their path length. Therefore, they have a high LET. While beta particles are charged, they have a -1 charge, so will interact less than alpha, but more vigorously than X or gamma rays. The lower the radiation's energy, the higher the radiation's LET will be. Diagnostic X-rays fall into the range of 26 kV for mammography to 130 kV in the case of CT, with day-to-day X-ray voltages falling somewhere in the middle. Tissue composition can affect LET. Tissues with a high atomic number will interact more vigorously with radiation, which explains why radiographs are able to visualize internal body structures like bone compared to the soft tissue in the organs. Here is a chart of typical LET values for common X-ray energies. Notice that as the energy of the beam increases, the LET decreases, but not by very much. This chart consists of common forms of radiation. Alpha, beta radiation have the highest LET values, and this is because they consist of charged particles, whereas gamma and X radiation are found at the bottom of the list because they consist of electromagnetic radiation and have no charge. Closely related to LET is the relative biological effect number. also called the RBE. Since different forms and energies of radiation damage tissues at different rates, it is reasonable to assume that just knowing the dose of the radiation does not tell the whole story when predicting a given dose's effect on the body. RBE takes two radiations and provides a multiplier to equate their relative biological effect on the human body. For example, let's suppose that radiation 1 has an LET value of 1 kV per micrometer. Compare this to radiation 2, which ionizes tissues at a rate of 0.2 kV per micrometer. If we divide 0.2 into 1, we come up with a number of 5. This means that any given absorbed dose, radiation 1 will do 5 times the damage compared to radiation 2. This is why an absorbed dose measured in grays can have a different effective dose value measured in sieverts when comparing different radiation effects. So, radiation 1 has an RBE of 5, radiation 2 has an RBE of 1. Since radiation 2 interacts with the atoms that make up the tissues less, it will penetrate structures further and more often, and therefore deposit less energy in the tissues. This ends my presentation on LET and RBE. Thank you for your attention.